Okay, let's do one last talk about radical reactions. And I want to first go back to an old reaction. If we took an alkene, treated with HCl, we would expect to get an addition reaction to occur, and that addition reaction would give us the more highly substituted halide, the secondary halide, and we would call this the Markovnikov product. And that Markovnikov regioselectivity would be driven by the fact that we want to put the carbocation in the more highly substituted side of the alkene when we protonate the alkene. Great, this is old chemistry. Now, let's change this up just a bit. What if we do, not chlorine, crazy, HCl, and now we're going to do the same reaction, but we're going to have a little bit of hydrogen peroxide in here. Hydrogen peroxide very often leads to radical pathways through decomposition of hydrogen peroxide, which we'll show in a second. What we'll get from this is actually the primary halide, the anti-Markovnikov product. Now the regioselectivity changes because we're no longer going through a carbocation in this reaction on the right. We're going through a radical. And so this is all driven by the stability of the radical, not the carbocation. So let's see exactly how this works. So let's look at it as a radical reaction. We have an initiation step. Our initiation step is going to start with hydrogen peroxide. And that hydrogen peroxide, even at room temperature, hydrogen peroxide begins to decompose, and we form two hydroxyl radicals. Hydroxyl radicals are incredibly highly reactive. And actually, in the presence of HCl, these hydroxyl radicals react with HCl, and they will form HOH, you might know it as water, plus a chlorine radical. And this chlorine radical is actually going to be our propagating radical. I've sort of bent the rules. I tacked in that extra step on our initiation step. And I'll be honest, I don't know what you call this extra step, but it's not really part of the propagation step, but technically it's not an initiation step. So it kind of gives us a bridge between initiation and propagation. So I'm not saying it's okay to do that, but I want to be transparent. Hey, I just kind of pulled a fast one on you. Okay, so now what happens is our alkene reacts with the chlorine radical. The chlorine radical attacks, and it's going to attack the terminal end of our alkene. That's not a steric thing. That just sets up, if we attack on the end of the alkene, then the radical ends up at the more highly substituted position. We form a secondary radical out of this instead of a primary radical. So that's our first propagation step. In our second propagation step, we're going to take this radical that we just formed, and this is going to react with HCl, and that HCl is going to give us the CH that we needed, and as a result, we're going to reform our radical. So if we add up these steps, the chlorine radical cancels, this alkyl radical cancels, and what we end up getting is our double bond reacting with HCl to form our terminal alkyl halide. And what goes on the initiation step typically doesn't show up in your overall reaction. Since the hydrogen peroxide is part of the initiation step, it doesn't show up in the net reaction. But it is required for this reaction to go through a radical process. Now, I'm not going to draw out the termination step, but the termination step is any two radicals on this slide combining with each other. So there's a lot of different possibilities we could form out of that. So this is the how we perform additions of something like HCl to an alkene, and how we can do this and access the anti-Markovnikov product. And this is actually a really synthetically useful reaction, and it's performed on industrial scales pretty regularly.